Now, the application, the next application, is going to involve some vector algebra. And so, you've all had this before, right? I mean, so my experience has been, though, that just because you've seen something once or a while back, then that doesn't mean you have it at your fingertips. So I'm going to quickly just kind of review some two-dimensional vector algebra. Actually, most of the vector algebra part will work in any Euclidean dimension. It won't necessarily work in a relativistic world, but Euclidean space, especially a two-dimensional, what we're going to try to do is apply the event graph methodology that we've been studying up to now to model entities that kind of move around. That's just sort of the immediate milestone in front of us. Up to now, most of the models that we've been looking at have been some variant of a queue. We've done customers and parts and machines and servers, and all of that is actually extremely valuable for many domains, even within DoD. But there are also situations where you want to model, agent-y types of things. Sort of agent models are, well, they were all the rage. Now the big thing is AI and machine learning and stuff like that. So who knows? It may be another Six Sigma and other. I may not remember Six Sigma. That was a big thing a while back. Anyway, regardless. So what we're going to do is just take the simplest possible situation, because some people who are kind of will model this in a different way, in the most kind of intuitive first step way, will sort of say, well, these events are kind of fine for queues and all that, but I need to model things that move around, and you can't do that with events. Well, in my world, that's fighting words. So, okay, so vector algebra. In two dimensions, our vectors are going to be two coordinates, x and y, or x1 and x2. Actually, we're often going to kind of vacillate between xy or x1, x2. So here's a vector in two space, represents like a point, two coordinates. And how do we operate on these? Well, we can add them. If I have two of them, and I say I want to add them together, then I add the two coordinates. And we can sort of think of that, if this is kind of the origin, and this is like one, oops, let me make another one here. So if I have these two vectors, then you add them up by adding the two coordinates, and so the sum would be the two of those. Another thing you can do is sort of stretch them. So if I have a vector like this, and I want to scale it by a certain amount, then that will either stretch or shrink it out to in the same direction. Now, operations on the main operation we're going to look at is the inner product. And the inner product is, or dot product, is simply the sum of the product of the two coordinates. The norm of a vector is the Euclidean length. So what is the length of this vector? And how do we compute it? We compute it by taking the sum of the squares of the two coordinates and taking the square root. And then another thing which comes up is that if I have a vector in a particular direction, but I want a unit vector in the same direction, that is, one whose length is 1, then obviously I simply take the coordinates of that vector and I divide each of the coordinates by the norm. And that's sort of a special case of scalar multiplication. In other words, the scalar that I'm multiplying is 1 over the norm. And are you familiar with this sort of double bar notation for the norm? No.
I've usually just seen this as single bars on either side.
Single bar. Okay, well, mine is twice as good. Double bar. Okay, so I use a double bar. So in your mind, you can erase one of the bars if you want. So just whatever you do. Okay, so this is all review, right?
I didn't know what a vector was till this class. So.
Okay. So here's the problem. So we want to just sort of model the simplest possible case. And you know, one of the reasons why I espouse this sort of iterative modeling process is kind of gets back to the virtue of laziness. So if at some point when you're trying to do something, if you hit a brick wall, then the question is, how much effort have you expended before you hit that wall? So if I'm trying to model things moving around in 3D with fancy terrain and weather and all kinds of different stuff, and I find I can't do it, then I will have to spend a whole lot of effort until I realize that it's a waste of time. On the other hand, if I can't take a simple entity in 2 dimensions and move it from one location to another using what the methodology that I have in front of me, if I fail in that, then I get sort of an early exit, as it were. So you might guess that there's not going to be an early exit because we are hopefully going to succeed in what we do here. And the idea is that as you build up things, and you may reach a point where it's not possible to take the next step. At least you have something. Okay, so here's the problem. I have a unit, and we're going to be in a flat, evidently, the more and more people are sort of believing the world is actually flat these days. I'm boggles the mind. But for a while, we're going to live in a flat Earth here. Okay, so, and hopefully, none of us will become actual flat earthers. But anyway, in many contexts, kind of the curvature of the Earth is not a factor in how things go. And again, remember, all models are wrong. Obviously, if we're modeling satellites that are orbiting, then a flat Earth model is probably not the best way to go. Okay, but let's come back to our flat Earth. We have a flat, featureless world in 2 dimensions, and at a particular time, and we can choose an arbitrary time. Let's choose time 0, and at time 0, it starts moving to a destination. We say we want to get there, and we're going to move with a constant velocity. Now remember that velocity is a vector and speed is a scalar, so you all know that. And so we want to be able to simulate this. And how is this done? Now the usual way uses what's called a time step. And you're probably all familiar with that, right? Yes, no? If you've encountered agent models, the chances are overwhelming that they have their agents move around according to a time step. And what's a time step? Time step is we have a certain increment of time, and every delta t time units, we click the clock and then update everybody's state. And then we click the clock again and update everybody's state. So the usual way to solve this kind of problem is figure out where the our unit will take a step after delta t and say, okay, after 0 plus delta t, we're here. At 2 delta t, we're here. 3 delta t, we're here. 4 delta t, and then we finally get to our destination. That's the way this works. Makes a lot of sense. Seems intuitive. Seems real easy. But there's a problem. And this is a non-vacuous problem. This problem actually exists in models. And the problem is that if my task is to move at a particular velocity, that is, at a particular speed in a particular direction, and I'm only allowed to move in certain increments which are dictated by the time step, then it may look like this. And again, this is not vacuous. This exists in pretty much every time step model. In 3D graphics models that have collisions, this is sometimes referred to as a collision problem, where basically what happens is you take a step and your ball has actually kind of gone into the wall because of the step that you're taking. In this particular case, what happens is if you simply kind of have a naive time step, which many are, then, and our task is to get to this place, then, as the saying goes, you can't get there from here. And there, a few years ago, I had a student who kind of actually explored the difference between modeling things with time step and modeling things as we're going to present. And in models that people were using, including models for their thesis, they found that this was a very real phenomenon, and that typically they would apply band-aids. So one band-aid they would do is realize that they'd overstepped a thing and then try to take a step back. And then depending on the size of the time step, sometimes that worked and sometimes it didn't. Okay, so that's, so basically this isn't what we're going to do. So just to actually motivated by even in this case, look, we have 1, 2, 3, 4, 5, 6, 7 times when we're just kind of doing stuff where we know what the answer is. And getting back to some of the original motivation for a discrete event, the idea is that if nothing is going to change, then why kind of take any cycles and spend them when you know that nothing has changed?
Because in a lot of contexts, something can happen to that object between point A and point B, and you want to be able to resolve that without having essentially just be non-interactive until it reaches the destination.
Okay, in your model though, if something happens, then something happens. But if nothing happens, then nothing happens. Encountering something is something happening, and that's a state transition.
But how do we know that thing happens? Like, if you're trying to capture some sort of like intersection or trajectory or whatever, yeah, you need to be able to query, like, where is this object? Where's object A? Where's object B? Like, it's not as clean, but I feel like in practice, it reduces the coupling and the logic required to have things like interactions in the path.
Well, it reduces how much you have to think.
That sounds like a virtue to me.
Yeah, yeah. Well, and how much you have to put into your model. In this world, there is nothing else. There is nothing this is going to encounter. So Now, if we can't do this, then you're right. Now, encountering something, that's obviously something we're going to have to deal with. But let's deal with the problem in front of us instead of the problem that's not in front of us. Okay, so in an event-driven world, instead of clicking the clock each time, which in my experience really, I see it really comes up with insecurities on the part of the modeler because, oh, something is going to happen. I'm worried that something's going to happen. So I'd better check because if I've taken a step and something has happened that I didn't realize, then it must have happened sometime in here. But you see, the problem that you say exists even here because I have jumped from this point to this point. And so you can ask the same question. What if something happened between the time that I jumped from here to here? And the problem here is that I have no way within this methodology of identifying what that is unless I step out of the methodology. In other words, in this world, time only exists at these discrete points. And anything that doesn't happen at these discrete points simply doesn't occur unless I step out of that.
Couldn't you just, you can interpolate from your position to the previous step and your current position, and then
Right.
It's
And that's stepping out of the methodology. The methodology is I click the clock by a certain amount. Now if you say, well, what if something happened in between? Well, I got to interpolate. Yeah, that's stepping out of the methodology. In other words, if you have to kind of put a Band-Aid on your methodology, then why not take a step back and approach it from a different angle? And this is the angle that we're going to approach it from. Now, hold on to that objection, and go with me here. Because in a discrete event world, if I am traveling at a certain velocity to try to reach a certain destination, then there are basically two events that I'm interested in. And again, if this is all I care about, then I'll call maybe the time when I start the move, a start move, and the time when I reach my destination, an end move. And all I need to know is how long is it going to take me to reach that destination. In between, I want the unit's location to be able to be captured exactly at any time. And this is not possible in a time step world, because in a time step world, the only times that I have are discrete, multiples of my time step.
So this isn't discrete then?
This is discrete event. The discrete modifier refers to events.
It sounds like we're stepping outside the methodology here.
The methodology is discrete event. So what is there about this event graph that is outside the discrete event methodology?
We want to find where that position is at any time. I mean, it's not just jumping right from the start to the end at any time. It could be anywhere in between the two, which is a continuous space. Or continuous time,
Yeah.
I guess. I mean, you say it's continuous motion right there.
Yeah. In using discrete events, we can model continuous motion in a way that time steps cannot. But we have to kind of, how shall I say, it's like, sometimes we can be so invested in a particular way of looking at things that we're not open to another point of view. So here's the conceptual issue which comes up when you live in a time step world. And that is that you're thinking of your location as the state. And that's sort of embodied in the last comment. Now here's the thing, is that if this unit is in continuous motion, then the location is changing continuously. And therefore, what that means, the implication is that location cannot be a discrete event state. Why? Because location is continuously changing. And discrete event states must be piecewise constant. Okay, so we're screwed. Or not. So let's see how we would define this as an event graph model. Well, the key has to do with how we're defining our states. If location cannot be a state, then I apply the visit to the doctor rule, which is you go to the doctor and say, what's the problem? He says, it hurts when I go like that. He says, well, don't go like that. So if location cannot be a discrete event state, then don't go like that. So what is the state? Well, if I'm at a particular location, and at a particular time, I start moving with a constant velocity v at sort of a time I'll call t naught, and I'm moving at a constant velocity, then at any time, well, first of all, are these three values going to stay the same throughout the maneuver? We better hope so, because I've defined them to be discrete event states. If I begin at a particular location and at a particular time at a constant velocity, then until I reach my destination, those quantities do not change. And so those three quantities are discrete event states. Now, if I'm headed for a particular destination, then that also might be something that I'd be interested in. And if, as long as I'm heading toward that destination, does that destination change? As long as I'm heading toward it. So what parameters do I need? Again, we're taking the simplest possible case here. So first of all, my unit has to start off somewhere. So I'll start off, and again here, x is a vector. And you may be used to, sometimes people like to put little arrows above or above their vectors. I don't. So actually, I took the line above vectors and I put them on the norm. So if you want to, in your mind, kind of move the line from the norm to the above the vectors. And again, we're looking at the simplest possible example of this. So we're going to have just some sort of constant speed. So obviously, when you start to get more complicated things, you know, we could have, well, here's my max speed, here's my cruising speed, here's how fast I'm going right now. Again, we're starting simple. And the question about location. So now here's the thing. In discrete event models, time is continuous. It is not discrete. I can ask at any time if an event occurs, I can have access to all of my states. So if I want to know where my unit is at any time t, then I can simply apply the equation of motion to my states and get the answer. Because if I am in a state where I've begun at this location, at this time, at this velocity, and it's now this time, then this equation gives me exactly where I am. Exactly. In other words, the location at any given time can be determined from the discrete event states. And so, what does that look like? Well, there is one, if you remember when we deal with numbers, there's this not a number thing, which is sort of convenient. And Here, unfortunately, Java doesn't provide something like this, but conceptually, it's useful to have something like not a number except for a point. And so not a point is going to be, and as we'll see in the implementation, it's just a point with coordinates that are not a number. Okay, so we have 4 state variables. We have the time that we start our maneuver. We have our initial, we have our current, the place where we last stopped, and that's initially going to be where our initial location is. We have our current velocity, and let's assume that we just sort of start with no velocity because we're just sitting there. And then we don't have a destination yet because nobody's given us one. So we're going to call our destination not a point.
Isn't this functionally just a time step, except the time step varies?
No.
Because we have the delay, which is, and we have, it's okay, it's going from point to point, where the points are x0 and d, with a delay of t sub m.
Well, the difference is, again, in time step, the increments of time are fixed. And they are determined by, in fact, in practice, they are determined by whatever the software decides. Typically, you can't, in fact, in most models, you can't even change that. In some, they let you change it, but once you change it, it's fixed. The difference is that this time can be anything. Not, in a time step world, the time between when that is, my locations can only be identified at discrete points, and the time between when one thing happens and another has to be a multiple of the time step. So no, this is not time step because there's no time step.
So what's that t sub m?
The time it takes to move from, well, it's defined right here. And it's the time it takes to move from here to here.
So the time it takes to step from point A to point B.
Well, you use the word step as if it were the same as a time step.
I'm not seeing how it's not.
Okay. So you're not. Okay, so what are the state transitions? Well, the first is that you decide that there's now a destination that you want. Okay, and I'll call that event a move to, and the argument is going to be some destination that somebody's going to tell you. And so the state transition is now the destination is whatever the argument is, and it will say, okay, now I want you to move to this destination. So now how do I move there? Well, first I need to figure out the velocity. So let's unpack this. If I am here and I want to move here, then the vector between here and there is simply the difference of the two. That's d minus x naught. The destination coordinates minus where I am. This is where I am. Now, but I want to go there now my speed is always going to be constant. That's a parameter. So I want to go at this vector. So I have a vector which is in the right direction but the wrong magnitude. So the magnitude of the velocity vector is your speed. And so how do you turn a vector of an arbitrary length into a vector of a given length? Well, one approach is you first turn it into a unit vector and then multiply it by the magnitude that you want. So to turn it into a unit vector, I divide by its norm, that is the norm of the difference between the two, and then I multiply by the speed. And that will give me a vector in the direction that I want to go at the speed that I want. Now the time that I'm starting is my current time, and I need to make sure to do that after I do the other. And the time it's going to take me to get there is going to be the distance divided by the speed. And when I get there, now all of a sudden, the last location where I stopped is now my destination. I'm actually exactly there. Now my velocity is 0, and now that I don't have a destination anymore, that's simply the, same, no destination. Okay, so to implement this, as it turns out, Java has a class called point2d, which, my philosophy is that if you have something, somebody have done something, and you should ideally use that. In this case, if it's in the language, then you're usually better off using it, even though the point2d class they created because their original point class kind of sucked. So they came up with a better one. In fact, they came up with a whole 2D framework, which is kind of another topic altogether. They used something a little bit, this is the only example of this particular structure in Java. It's just the guy who wrote it probably just had his, this way of doing it. The way they implemented it is they implemented point2d as an abstract class, and then they wrote 2 static inner classes that implemented the remaining methods. And the difference, the 2 are point2d double and point2d float. Now, I know that in certain graphics contexts they like to use float because it saves a little bit of space. The problem is that for the kind of computations that we need to do, float is just not good enough. Double is barely good enough. But float is absolutely just not. So we use, the implementations are point2d doubles, but if for some reason somebody wants to use a float, we try not to be too restrictive in that. So we will typically define our variables as point2ds and implement them as point2d doubles. Now, so they do have some helpful methods. So they have a get x and get y. So if I have a point2d, I can get its x and y coordinates. It has 2 very convenient overloaded methods. Okay, first is set location, and if I give it another point, what it will do is it will set the coordinates of my point2d to the coordinates of the other point2d. That can be very helpful. Or I can simply set the location to the coordinates that I give it. So those are 2 very useful methods. And then finally, since these are objects, and if you remember, we, especially when dealing with state variables, we have to be a little bit careful in terms of encapsulation. So when it comes to setters and getters, for example, we will typically want to return a copy. And point2ds have a clone method that will return a copy of themselves. And the problem is that there must be some internal reason why they didn't implement it using generics. But the clone method in point2ds, they return a copy, but the type is object. So when we use clone on point2ds, we will typically have to cast it to a point2d, which is kind of a little bit of a pain, but not horrible. I want to quickly implement this. And let's, hopefully you won't do bad things to me. Let's see, did it get through? All right, so there it is. Okay, so in the class code, there's another sub package called mover because we're going to put a bunch of stuff there, and really this is this. What the heck is that? Okay, a couple things. This isn't the commented. Oh, well, I'll update the commented when I. Okay, a couple things. One is here's this not a point thing that it would be nice if Java provided that. They didn't, so I did. And then sometimes it's helpful just to have a 0 point. So I got one of those. So that's just sort of aside from the whole thing. But we have 2 parameters. And again, what are our parameters? Our parameters are the initial location and the constant speed, and I call those the initial location. I'm calling it a max speed. Just could call it anything like that. Again, setters and getters for these. 4 state variables. So what I'm calling the last stop location, this is the place where my unit will stop. Velocity, again, a point 2D, because velocities are vectors. And then the current destination, again, another point 2D. And then what I'm calling my start move time, which is just going to be the time when I start moving. So again, master constructor with the 2 parameters. And then my 0 argument constructor, what I've done is, again, just to instantiate, this is just to instantiate it. So just sort of a little SimKit aside is this, remember, this will kind of come up once we start doing multiple replications, is that you want to make sure that it's the reset method that will initialize your state variables, or the init for loop. So this is simply to instantiate the state variable objects. But then on the reset method, I want to set my velocity to 0, so I can set its location to the 0 point. Again, you want to be careful I don't want to set it equal to that, because that would also break encapsulation. I want to set the location of my last stop location to the initial location. Why? Where did that come from? That directly came from my run method of the event graph. Velocity is 0. The current destination is, again, the coordinates of not a point, and then my start move time is going to be the sim time. And I know in the event graph it sort of said 0. This is going to be 0 pretty much always. So that I could set that to 0. That wouldn't be a problem. Okay, and then notice that the event graph itself does not. The run doesn't schedule anything, so all it's going to do is just fire the property changes. So that's kind of a given. All right, so here, move to. What does move to do? Move to simply sets my destination to what the argument is. So if I say move here, then again, the old set the location and fire the property change, and then I schedule the start move event with a 0 delay. Now here's where I have to do a bunch of calculations. So here first I need to figure out what the velocity is. So to do that, I need to subtract the destination from the current location, divide by the unit vector, and then multiplied by the speed. So it would be nice if Java's point2Ds did that, but in the graphics they never bother doing this, so we have to kind of do this by hand. So first, I take the difference. This temp is just the difference. Maybe I should have named it better, like difference vector or something like that. The distance now is going to be the distance between, actually the point2Ds have a distance method, and that will give you the Euclidean distance between your point and the point in the argument. So the Euclidean distance, now they don't have a norm. That would be nice, but they don't. But the norm is simply the distance, the Euclidean distance between your point and the 0 vector. And I have this 0 point that why I have that? Because it comes up like in situations like this. This will give me the distance between my current location and the destination. And then the x-coordinate of my temp variable, the difference, times the max speed divided by the distance. That is simply that will give me the coordinates for my velocity vector. And so now my temp, that should have had a better name, now is the velocity vector. So now I can get the old one, set the location of my velocity, and then fire the property change. Similarly, now I need to, my start move time is now my current time, because the last time, remember, it was initialized to 0, and this might be sometime later. So I simply do that. And then the move time, again, I've computed the distance, so I can kind of just reuse that. The distance over the maximum speed is the time it takes to do that. So I can simply schedule the end move event after that move time. And what does end move do? It just sets my location to my destination. My velocity is now 0, and my destination is now not a point. And that's basically it. Now the other, as I mentioned, in order to preserve encapsulation, our getters should return copies of things. And so this is the way that there are several ways to do it, but this is kind of the easiest. Simply clone it, and I have to cast it to a point 2D, because the clone method unlike the array, remember when we used arrays, they were clever enough so that if I clone an array, the return is an array of exactly the right kind, and that was nice. For some reason, they didn't do that in objects in general. There must be some technical reason for that. I'm not sure why. But again, it's all the setters and getters for these. Again, yeah, the other thing is that our setter for max speed needs to be sure that it's not less than 0. So now I could set a max speed of 0, and that way it would never be able to move, of course. But and sometimes that, believe it or not, that's sometimes something that might be useful. But certainly a speed of a negative speed has no meaning. So if I try to do that, then I should say no. It would be nice if Java had a richer set of types. So for example, if it had like a non-negative double, that would be nice, but it doesn't. There must be languages that have more robust type. Okay, so there it is, and I can see that I'm out of time, so we'll have to wait till tomorrow to see whether this thing actually works.